Thank you.
And I would like to welcome Alexander Vallejo, who is a PhD candidate and commercial coordinator of the Santo Domingo Institute of Technology. And his background is that he has been a professor for more than 12 years and he has a quite big experience in the field, and he's focusing a lot in urban wind development. Alexander, are you there?
Yes, good afternoon, everyone. I'm here. I'm sharing my screen. Please confirm. Okay. Let me set. Okay. Okay. Thank you. Good morning, everyone, and good afternoon. Thanks for the invitation to the Nordic Folkecenter and the sponsor. Here we can share in the urban wind assessment with the potential in Dominican Republic, and with the second phase of the presentation, we will discuss some hypotheses about the resilience approach. Okay. This is the agenda, mainly the characterization of the study area, the urban wind energy assessment, urban wind energy turbine to be selected, wind energy potential and environmental evaluation, and a little bit with the economic evaluation and the resilience assessment, and some conclusions and recommendations. Here, as we know, the purpose to have the wind energy in the urban area is to decoupling the fossil fuel in the matrix of the mix and have the independent with the economic expansion. We have here to some issue in the urban planning with the heat islands as well in the Caribbean countries. Another is to be aligned with the commitment with the emission reductions to 2030 in DR based on the 2010 years emissions. And this the generation like the smart wind turbines, PV, solar technology have the technologies we can deal with and contribution to that targets. And as well as the consumption is in the urban zone, in the buildings are pretty high due to the immigration from the rural zone to the urban zone in emerging countries. As well, we can see in the picture the categorization with the urban technology, especially the wind turbines, smart wind turbines. In the system, in the urban zone, we have a standalone near the buildings. We have to retrofit it to the existing buildings, and we can fully integrate with the building. Is the architectural design. Okay, here we have some introduction with the DR. We are an emerging country. We have the prospection in two major cities. In Santo Domingo is the capital, and the San Cristobal is near to the Santo Domingo. Here we can see the Santo Domingo in the map. And the GDP is near to $88 billion. In recent years, the DR have the major growth in the region with the GDP. And we have near to 10 million inhabitants. And here we have some panoramic view from the Santo Domingo, and we can see the deployment buildings have been increasing in 10 years ago. So according to the trends, we have in the left side the distribution of the location of the CFD simulation according to forecasting the wind urban assessment. So we can see in the tropical zone we have a very low investigation in this way. So we think that it's very important to investigate and simulate the energy potential, especially in the tropical zone, or so in the Caribbean area. So the methodology presented in many works have mainly these 4 steps with the building data collection, with the wind energy, speed, and characterization, and the turbine selection, and the annual energy wind assessment to estimation. So Reseja have a very great works in this way, very adequate to our investigation. So we have some, let me say, okay. Okay, we have here the illustration from our main steps recommended to the carry on the investigation in the Caribbean. We have the first 4 ones have the same included in some investigation, the characterization of the study area and selection of the cities, wind energy assessment, the smart wind turbine selection, annual energy production estimation. We have another 2 main phase or steps with the environmental evaluation and the resilience assessment. So you know the environmental evaluation is in order to the CO2 emission reductions, and the resilience evaluation or assessment is in order to have in account our condition with the events with the tropical and hurricane that will affect frequently our countries in the Caribbean. Okay, about the characterization of the study, we can find some tools with free access provided by HIS in the internet, like skyscrapers. We have rapidly the some buildings that can meet our requirement, for example 10 meters over the ground, and we can place turbines in the building. So we have identified with 3 anemometers, 2 anemometers in Santo Domingo, and 1 located in San Cristobal. We simulate the installation of 5 small wind turbines in each and height of the respective anemometers. For example, we identify 95 buildings in Santo Domingo with a height with the first anemometer in Santo Domingo, and the second one anemometer have also 95 buildings. And in San Cristobal, we don't have his information, but we estimate by looking at 25 buildings. Okay, several methods are used to wind forecasting, and each have the owner advantage and disadvantage, and the combination of some of those methods have the best result to the energy estimation. So we have to validate each. Mainly, we recommend for our country these 3 ones, from the mesoscale to microscale according to spatial and resolution. We recommend the numerical weather prediction, also as well known as HIL. After that, with the on-site measurement, and after the computational fluidic dynamics and CFD, because we start in the big picture and go to the high resolution in the spatial condition. And I think that is cost effective to our condition, because the wind tunnel is very expensive and the analytical methods are very complicated and has been reported some errors because the performance of the turbine that accepts the best limit, because it's not real. And the wind turbine have the errors around the 5 or 20% reporting in some papers. The numerical weather prediction have a very resolution according the time. So we can find information for many years. However, we can find the information with high resolution or short time, because we can find the information with minute by minute or 50 minute by 50 minute. No, normally the information appears 3 hours with separation. So many techniques has been included to complete the gaps in one recording and others when it's the 3 hours and 3 hours. Here we can see our on-site wind energy and prospection system. We have here in the INTEC, we have one anemometer here and another here. Hello, can you hear me?
Yes, we lost you for a moment.
Okay, sorry. Maybe we have energy loss here. Can you see my screen?
Not yet.
Okay, let me share again.
The way. Yes, wind energy assessment.
Okay. Okay, so here we can see the wind energy assessment for our investigation, and we can see the monthly average wind speed when in the summer we have the highest value, near to November is going down. So we have 3 anemometers installed, one in the INTEC in recording data from 2017, and the second one in the INTEC recording data from the same year, and the last one is located in Loyola in 2020. So here we count the wind rows. We have the main duration from the north according to the 0 degree. Okay, here we have the diurnal average wind speed. With each column, we have an independent colorful scale, and we see the main average wind speed is around the 13 to the 15 hours in each day. We apply the ISC standard according this investigation. Okay, according the distribution, wave distribution, we have some plotted, and here we have each curve have the same area, and with the anemometer 2 we have the best area over the high wind speed. However, we have an average wind speed and consider low for each location. According the turbulence intensity, we have identify with each anemometer the low intensity turbulence intensity, the moderate turbulence intensity, and the highest turbulence intensities according the NRL's consideration. And we have in the major time the moderate turbulence intensity. Okay, according the wind turbine energy selection, we have used wind turbine recommended by RESEIA in a recent investigation. You know, when you have a low wind speed, the suitable wind turbines are the vertical axis wind turbine, because
when we work online, these things can happen. So let's see if so it seems she is back.
Hello.
Hello. Maybe you should keep the just keep the camera closed, because then it's easier for the connection.
Okay. I have an energy loss here. Sorry.
Yeah.
Can we continue?
Yeah.
Okay. Sorry, everyone.
Can happen.
Okay. Here we are talking about the wind turbine selection. You know, when you have low wind speed, it's recommended the vertical axis wind turbine, because can be there very well with the low wind speed. And horizontal axis wind turbine generally have been installed in separate space, and can have more inadequate with the wind energy duration changing a lot. Here in this chart, we can see the power curve of the wind turbine illustrated here by RESEIA. We have feeding by the regression to estimate our power production with our wind speed in the air. Normally, the annual power of the energy generated by the wind turbine is simulated with the height of each sensor here in the position. We consider 5 vertical axis wind turbine per building. We have 2,050 buildings in both cities. So the total is 215 buildings, and the total is 1,015 wind turbine in each for those cities. And as we can see here, we start from 2 meters per second to near 11 meters per second. We have energy density here, like the most unsuitable energy are between the 2 to 4 meters per second, and we expect near an estimation to one house to 215 kilowatt per month in the consumptions in our country. According to the environmental evaluation, we have a national interconnected electrical system in this chart in the left side, with the emission generation by primary energy fuels in 2020. And here we have very fuels and fossil fuels metrics with the coal-fired power plants by the coal and the NG or turbines. We now the natural gas have been in the last 10 years increasing in the air. So the renewable energy we have here, the wind and the PV and the hydro. So we have implemented to determine the CO2 emission according to the standardized baseline in the United Nations Framework Convention on climate change. Is adopted this indicator with the 0.16 tons per kilowatt per megawatt hours. According our estimation, we have an annual energy by small wind turbine 254, 342, and 119 seats. And it's the number of the wind turbines and the number of the building, and the total energy estimate is near to 317 megawatt hours in the year, and the equivalent 197 tons per year of the avoided CO2 emission to the planet. According to the estimation, economic estimation, we have the cost of the urban energy is a very key factor to the optimal consideration by the physical and financial and leverage in the entire system. Considering the cost of the central generation, the generation cost, the capacity payment, the auxiliary service like balancing power and transmission and distribution costs, energy loss. Here in the Dominican Republic, the energy loss is very high. We have huge of the millions of dollars to subsidize the electricity subsector. So in this estimation, the cost of the energy in the last year was 30 cents of dollar per kilowatt hour, and the preliminary assessment of the LCOE with the wind turbines quote by Chinese pro suppliers, we have that the cost levelized of the wind turbines is near 7 times more with the grid electricity price in the year. So we have consideration investment for one turbines, the estimate operational maintenance cost and the investment rate and the lifetime to 20 years. And the estimate annual produce is near to 3 megawatt hours per year. Okay, according the resilient, we have located in the Caribbean. As you can see here, we have so many tracks from hurricane from 1993 and 2020, according to the NOAA. And here we have some tracks for this year. So you can see we can analyze the hazard from these events. According to the resilient, we have mainly some for categorization that be very important to have in account with the anticipation of the disruptive events in one of the most important to electrical systems. We have to increase the robustness of the system by prediction. In order we can predict the problem, and we can anticipate responding to configure everything. Another phase is the absorptions. Is an absorptive capacity is defined to the ability of the system to withstand the turbulent conditions. And here we can see the adaptations is the capacity defined to the degree in which the system can self-organize and overcoming of disruptive events and keep running accordingly. And recovery is the go back and restorative capacity to repair and go back to the standard condition. So these are here the main phase in the energy system resilience. This graph show the first one, the conceptual multi-phase of the energy resilience of the resilient trapezoid. We have to implement to our investigation this concept in order to estimate the engineering phase. You know, when you have the 100% robustness of the system, and when we have a hazard, the engineering resilient have to preserve the operation. So with the operational is go deeper in the performance on the system. After the engineering, the operational have maybe one operator and the human cooperation to the system to keep running with low performance. And another one is the community. When the system go to very low performance, but is keeping running, we can keep in this stage. And obviously, we need to another human modification, organization, society, etc., to restore the system again to the nominal operation. Here we can have some metrics. So this is very important with the anticipation. In our case, we are talking about the hurricane on tropical storm in the Dominican Republic. So the prediction is very key factor to our take a decision of the disassembled or keep running the small wind turbines. And another, this is the first phase or stage to prepare. And here we have the hurricane. We have to the area here to the windstorm, the hazards. And here we have the adapt the system to the hazard. Maybe this area have in time, maybe hours or minutes, we have to determine. And after the adaptive area, we have a recover area to keep the system again back. Okay, this table have summary of theoretical resilient metrics or each phase. As mentioned before, prepare, withstand, adapt, and recover have metrics and each unit for those. We can measure in hours or another indicator like performance by hour or kilowatt by hours, etc. Here we have our hypothesis to demonstration. We have the power and the time with an amplified simulation. In this case, we have for example, our smart wind turbine with the wind speed of 15 meters per second. We have when we have this wind speed, the smart wind turbine is go out, and we don't consider the disinstallation of the wind turbine. The wind turbine could have a cut wind with the 15 meters per second. However, maybe can withstand more wind speed. The wind turbine cannot have a structural loss or damage. And in this case, we are simulating the wind turbine with the same cut out wind speed. And however, we are considering the assembly and assembly after the hazard. For example, when the wind turbine, we expect to high wind speed, we need to disassemble the wind turbines in the building. We have to estimate this time to be adequate to disinstall, and after the events, we restore the smart wind turbine system. So in this case, we have the scenario with the same condition, and here we don't have anything, and the smart wind turbine maybe go down and can have a damage by the hazard of the tropical storm and hurricane. All energy in gray is energy loss, and the system is not go back because it's very affected. So these are very approximation to our condition, and we are working about these themes. In our conclusions in this research, we are starting point to the accessing of the urban energy potential in the Dominican Republic in order to contribute to the decarbonization of the country, because we have many capacity. If in the net metering is only PV technology, and we want to include the urban wind energy to consideration and planning. And another, we have low wind speed in our research identified to our 3 locations. We estimate 3 megawatt per year, 300 megawatt per year. We recommend to quantify the potential of the buildings detailed in terms of the number of the building and surface available to install a wind turbine. So in the future, we recommend go in deeper with this resilient analysis to our system. Obviously, policies and incentive as needed to the local market in DR. So thank you very much for your time, and we are open to receive recommendation and collaboration. Here are some reference according we have checked for this presentation. Thank you.
Sorry. So I was saying thank you to Alexander, and yeah, apparently I was muted, so I will repeat. We don't have much time for questions. If there is any question, you can put them on the chat, of course. But with that, I would like to thank you, Alexander.